I'm happy to welcome Isobel Ojalvo here to Brown for the colloquium. Isobel is got her PhD at University of Wisconsin in Madison, and she's now an assistant professor at Princeton. And in between, she was a Dickey Fellow at Princeton, and she was an LPC Distinguished Researcher, I think, and now she's the LPC Coordinator, actually. The LPC is the Physics Center, LPC Physics Center, the Large Hadron Collider Physics Center at Fermilab. And she's worked on Tau object ID and trigger and level 1 trigger software on CMS, and obviously made a big contribution to CMS. I think she's one of our rising stars at CMS, so let's welcome her for this colloquium. And
Thank you so much. Yeah, it's really lovely to be back here at Brown. I came a couple of times already for Snowmass, and yeah, I really appreciate the group here. I got a very warm welcome today. It was very nice talking to everybody. And yeah, and thank you so much. I've really enjoyed interacting with the physics department here over the years. Right, so today I am talking about, well, I'll give you an introduction to what my group does overall. I'll give you an introduction to the LHC and the CMS experiment. How many people have seen a CMS talk, or Alice or CMS talk recently? How many people haven't seen a CMS talk ever? Recently? How many undergrads do we have? A couple. Oh, we have some undergrads. Okay, cool. So I do try to make this somewhat accessible for all sorts of, from all sorts of backgrounds. If there's anything actually as undergrads that you guys do not get or you think could be better explained, do feel free to let me know, because I do try to make the colloquium enjoyable for people from all different backgrounds. Right, so I'm Isobel Ojalvo. I am a professor at Princeton University. And I have primarily been working on, for my detector work, I've been primarily working on this system called the trigger system. The trigger system is responsible for deciding what we're collecting at CMS, and has to do that in a very, very short period of time. So I'll be discussing that today. Here we actually have an event display from the CMS detector. It's a event that we collected with this new algorithm that we'll be talking about today, which we put online. And so one thing that's interesting about the Large Hadron Collider is that we have built a QCD machine to try to discover electroweak physics. And so you can imagine that if we have lots and lots of QCD that is being created at the LHC. It's something that we need to carefully think about what we're actually going to be collecting. And so I'll be discussing how we are trying to change the way that we are discovering new physics at the LHC, and hopefully, and eventually the HL-LHC, and hopefully I will tell you why this is exciting and why you might want to go into this area of research, and convince you that what we're doing at CMS is currently just the first step on the road to making our systems more intelligence and bringing intelligence closer upstream and closer to the actual physics at these detectors. Okay, so I'll just give you a quick overview of what I do and what my group does. So this is my group. A couple of them have graduated. Stephanie has gone on to Colorado University Boulder. I have one person actually went from working with me on anomaly detection, which is the primary subject of the talk today, to working at Thomson Reuters. I have a CERN fellow, a Columbia Data Science fellow, and somebody going on to Red Violet, also doing anomaly detection. But the majority of my group is working either on the trigger system, Higgs to tau analyses, or future colliders. If you have time, I'm happy to discuss my work on the 10 TeV muon collider and our Maya studies, even though it's not the subject of the talk today. So here we have the Large Hadron Collider. It is a proton-proton collider with the highest center of mass energy of any particle collider ever built. You can see, so my experiment over here, our experiment, we have a number of CMS people in the room, is located over here. We have the ATLAS experiment over there. We have multiple rings where the protons are being accelerated, and then finally accelerated to their final center of mass energy of 13.6 TeV and collided within the LHC. So from the core, the guts of the experiment, essentially we have two beams of protons that are accelerating in opposite directions, and then they're made to collide at these various interaction points. So at CMS, at Atlas, LHCb, and ELISE. And by studying those interactions, we're able to look at a wide variety of different physics or different particle physics reactions. And so when we have these protons are made up of partons, which are mixes of quarks and gluons. And maybe you're familiar with these parton distribution functions, which basically tell us what's the probability of seeing some sort of quark with a certain energy. The beautiful thing about seeing this distribution of different types of quarks at different energies is that it gives us access to a very, very wide variety of physics. So here on the right-hand side, this is something we always show in trigger talks. On the x-axis, we have the center of mass energy in TeV. On the y-axis, we have the cross-section, which is basically the likelihood that a given reaction is going to take place. And so here maybe we have a 1 TeV proton-proton collision, 7 TeV, 10 TeV, 13.6 TeV, which is where we're at now. Maybe if we go higher energies as well, we look to see the different processes and how likely they are to happen. Maybe I will use my stick here since it's pretty high. So this is the total cross section. So the likelihood of two protons interacting with each other at the LHC. Here we have the cross section for single B production. Down here we have W electroweak physics like W bosons and Z bosons. So this is something that we want to study quite a lot. And of course we know about the Higgs was discovered in 2012 at the LHC. And you can see multiple orders of magnitude. So all the way up here, something like 10 orders of magnitude between our overall inelastic cross-section to something like Higgs production at the LHC. So what this tells us is that Higgs production at the LHC is extremely, extremely rare. And it's very difficult to pick up exactly what we want. Even trying to get something like a W or a Z boson, which is also interesting to study for a wide variety of reasons, or my favorite signature is Z to tau tau or Higgs to tau tau tau. It's quite difficult, and we have to, and so occurring very, very rarely, which means that we want a very large number of collisions if we actually want to detect any of these things. Here's an image of the CMS detector. It is basically a number of detectors in this concentric rings, kind of like an onion. We have the tracking system, we have the electromagnetic calorimeter, we have the hadronic calorimeter, we have this nice solenoid which bends everything so that we can figure out the particle trajectories. And then we have the muon systems. We have the goal of this, of course, is to be able to reconstruct very well these particles which are colliding in the center of this detector and be able to study the trajectories of the particles coming up. What does that mean? That means a huge, huge, huge number of channels. So millions upon millions of channels. And so each time we have a collision at the LHC, we have something on the order of 5 megabytes worth of data that is going to be produced. So I have a nice graphic over here. Which detector is this that we're looking at now? Is it CMS? No, it's not. It's Atlas. I couldn't find a good one for CMS. So here we have a nice image of the CMS detector. You can see these bunches of protons the Atlas detector. You can see these nice, it gets a point across regardless, protons that are interacting within the detector at every 25 nanoseconds. And then you have basically particle collisions and a spray of particles coming out, and you want to try to collect and reconstruct all the information that's coming out. Of course, we have a problem, and the problem is it's a massive, massive amount of data. So bunches collide every 25 nanoseconds, or approximately 40 megahertz. We have approximately 5 megabytes of data per bunch crossing, which means that we have 5 megabytes, let's say 40 megahertz, at a 40 megahertz bunch crossing rate. Let's say we have 90 days of uptime per year, hundreds of terabytes of data per second, or 1.6 zettabytes of data per year, more or less. Okay, depending on how much data we get out of each collision. But okay, we're just doing order of magnitude calculations here. 1.6 zettabytes worth of data per year is it's 10 to the 21. There's 10 to the 21 approximately grains of sand on Earth. So you can imagine this is a huge, really big data problem. And so, for one thing, it's almost too much data. We don't actually want to collect all this data. A lot of this is QCD, or maybe we do, but this is another issue that we can discuss. If we are interested in studying electroweak and Higgs physics, we only want to collect and study a subset of that data. And so to actually take this and make a fast decision of what we want to study, we use what's called the level 1 trigger system. So level 1 trigger system over here. So basically these FPGAs sitting on these generic trigger boards, they're fast algorithms. The reason we pick FPGAs is because we can control them at the level of even controlling all of the data I/O and thinking about exactly what circuits we want to connect. I'll discuss that in into that in more detail in a couple of slides. You see these blue fibers that are coming out. These are gigabit per second fiber optics. If you unplug them, don't look directly at them. You'll burn out your retina. These are actually, state of the art at the time data transfer mechanism. So, the calorimeter trigger, which will be the primary focus of what I'm talking about today, sees about 4 kilobytes worth of data per event. And so again, to put that into perspective, we have to process something on the order of 200 gigabytes per second, which is on the order of something like scanning through 200 high-definition movies per second to only pick out, for instance, the pictures of the person in the red sweater. Okay, so you just imagine this is huge, massive amounts of data, and to be able to do something like that, but to be able to do that sort of level of filtering, we need very specialized, highly constrained computing devices. And then finally, I'll just flash one more word about this to set up the overall story here, is that the data stored on the detector, is stored on the detector until it's told to be triggered. And we can only save about 0.25% of the events. So very, 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 very small fraction. Due to the constraints of computing, what we think we'll be able to reconstruct, due to the detector readout. And so we have to do a huge amount of filtering before we're actually able to, we have to filter a large number of events before we can actually read out the detector. So just to recap, we have 3 things. We have 5 megabytes of data per event. We have 40 megahertz worth of data rate. So this adds up to hundreds of terabytes per second. And we have something on the order of only 3.5 microseconds to be able to process this data before we actually make a decision about the 99% of the data we want to throw out and the less than 1% of data, less than 0.1% of data that we actually want to, less than 1% of data that we actually want to keep. And so just to give you an idea of where this happens, here is our experimental cavern here. The counting room is actually physically close by to the experimental cavern because it takes time. Like when you're talking about the speed of light, you're talking about fibers. It takes time to actually transfer this data from the experimental cavern to the counting room. So when we only have 3.5 microseconds, it actually is beneficial to you if you only have to travel hundreds of meters to process that data. And so here's the CMS detector here, and the counting room right next door where a lot of this, where the filtering actually takes place. Okay, so I'm almost done setting this up. I'll just do a couple of more slides, a couple more thoughts about why we are looking for new mechanisms of triggering, and thinking about how we are filtering this data. So just to go into some recent history, when we went online, when we were building the LHC and we were going online, our purpose was 2 things. So one, we already had the WMZ bosons discovered in 1984, but the mystery for how they acquired mass seemed to imply that there should be something along the lines of a Higgs mechanism. So we had this idea that the Higgs would likely be discovered at the LHC, although there was no guarantee. We were also looking for things like supersymmetry. So we were looking for high energy deposits. We were looking for Higgs sort of physics, and and we basically just designed our CMS and Atlas detectors, and as well as our trigger systems around this. We managed to discover the Higgs in actually very shortly after turning online, which was a huge success. I joined the CMS detector or the CMS experiment. My first year at CERN was in 2011, so I got to be there in 2012 when the Higgs was discovered. But really, a huge success of my predecessors to be able to discover the Higgs so quickly and with such accuracy in both experiments at the same timeline. Fantastic achievement. Showed that the legacy systems that were sent up, that were put online, really just did an amazing job, really. Like, you couldn't have asked for, I don't know. It's, as we're going on to putting onto our next, speaking a little bit to my CMS collaborators, as we're going towards, putting things online for the HL-LHC, I am even more and more impressed by the fact that they were able to get things online and running and discover things so quickly. It's really an impressive achievement. So we were able to discover the Higgs, but what about the fermions? So at the end of run 1, we had some evidence of Higgs to tau with a single experiment. So this was an analysis I worked on, but we weren't able to get there to observation level with a single experiment. If you combine CMS and Atlas, you could get to Higgs to tau. And actually, I've been criticized for this in the past, so I will take a second and back up. This is the Higgs boson. Why do we know it's the Higgs boson?
At 125?
125 GeV, exactly. So these are invariant mass plots. We see this nice peak at 125 GeV. We have the Higgs decay into 2 Z bosons and then to 4 leptons. It should give us a very nice tight peak at 125 GeV. We have a Z boson over here at 90 GeV. Similar for Higgs to tau, we have a Z boson over here. Okay, it's around 90 GeV. But then when you go for Higgs to tau and add in some missing MET calculations, again, we can have a bump around 125 GeV. And you have something like the number of events per bin on the y-axis, and we have the invariant mass of the objects on the x-axis. Z to tau here, so in yellow, TT bar, electroweak, QCD, some of our backgrounds. And then if you subtract all of the backgrounds from our data, you can just start to see a little bit of a signal peak there for Higgs to tau. So we were able to discover that at the end of run 2. At the end of run 1, we were able to see an observation. But then at the end of run 2, we had the opportunity to actually look to install the phase 1 upgrade. So that we went from a legacy trigger system to these FPGAs, these high-speed links with these general field reprogrammable gate arrays. And then with that, we were able to discover we were able to improve our trigger efficiency and get a much higher efficiency for detecting taus online than we had previously. And this is where maybe I'll stop for a second, just tell a story that at the time I was actually a graduate student and creating some of these plots for what we could possibly do with the upgraded system. And at the time I actually, I was just a graduate student at the University of Wisconsin. I think it was around Thanksgiving, my advisor comes into my office and tells me that, the postdoc in the group is actually not doing so well. He has to go back to the U.S. He has to get some treatment for a medical issue, and so he's going to be quitting the group. And I was in I was a little bit into my 4th year of graduate school. And he's like, so do you want to take over and be our postdoc and work on this upgrade that's going to take a lot of time and be very, we have to complete it in basically a year and a half. We're under a lot of stress. Are you interested in that? And immediately I thought back to a time I was a ballerina and I was standing on stage and there were dancers all around me. And the lead ballerina, she actually runs off the stage sick. And I'm sitting there, just like 12 years old or something. And I'm like, okay, well, we kind of finish our dance and whatever and leave. And at the end of all of that, my ballet teacher tells me, what are you doing? He yelled at all of us. Like, we had, 6, 7, 8 little ballerinas, all 10, 11 years old. what are you doing? Why didn't you guys do anything? And we're like, what are you talking about? Like, you all had an opportunity. You all had an opportunity to replace the lead ballerina in action on stage. You should have just got up, started dancing, and you would have been the lead ballerina. Maybe you would have been the lead ballerina for the rest of, for the rest of the time. And he said that this has happened before in the past. And so when my advisor came into my office and was like, would you like to replace this postdoc? I was like, yes, I can make up for this, for my mistakes in the past. And I said, yes, I want to do this job. I would like to work on the trigger system. I will be the person and I will make this go online. And so that is what we did. We put the trigger system online, and we were able to actually observe Higgs to tau tau with a single experiment. Around 2018, 2019, I believe we got 2017, 2018, we got this single observation experiment out with the new trigger system, which I put online. And yeah, just to show one more plot, you can really see it. This is directly because of the upgrade. You can see here, Higgs to tau tau, this nice little difference between the data and the background. And that was my contribution to the analysis. And so then when I became faculty member at Princeton, I was like, okay, I need to find something that, we have a short period of time. I need to make a credible mark on this field. And of course, we look at all this and we see all the success from the standard model, but at the end of run 2, here we are, now we're at the end of run 3, but when I started, we're at the end of run 2, and we couldn't think, we have all these places we can still look, but we still are not there in terms of getting new physics. So it was a big question of what else were we going to do? So now for the second half of my talk, basically I'll give you a little bit of motivation for why we actually wanted to shake up our discovery methods at the LHC and the HL-LHC. I'll talk about machine learning and autoencoders, talk about our new algorithm, and maybe if I have time I'll get into some of the hardware implementation. If I don't, I'll skip over it and feel free to ask me later. So what does a trigger normally look for? So like I said, we're interested in electroweak physics, we're interested in Higgs physics. With Higgs physics, you have couplings to different particles. So you will have a Higgs, it'll decay to 2 Z bosons. After we get those 2 Z bosons, we're looking for 2 muons, 2 electrons. That's what the Z's will decay to. You might be looking for Higgs to tau tau. You might see a hadronic tau, you might see a leptonically decaying tau. You might be looking for Higgs VB, that's going to be jet. So these are all going to give you different sorts of decays and different sorts of signatures in the detector, okay? And like I said, due to these hardware constraints, we can only save a very small number of these events, or 0.25%. And so these are basically the particles. The particles that we know are the ones that we're looking for. And so the question is still, like, what if we are missing something? So in general, this is what a normal background looks like or normal QCD event looks like at the LHC. This is what a Higgs to tau tau event looks like at the LHC. So these very nice two-dimensional images. With a QCD, you see more of an even display or an even distribution in the background. With something that's Higgs, you might see some more narrow distributions of energy deposits, which is possible to make an algorithm with and to look at for online. But of course, we still have all these open questions. Why is the Higgs so light? Why are there so many particles and so few antiparticles? What is the nature of dark matter? And so for years and years and years, we've been able to try to look directly for all of these theories, and we've performed all these different sorts of searches to try to answer these questions. But the question remains, are we unlucky? Or are we simply missing something? So is there something in those backgrounds that we haven't been able to eke out yet? And so that has been my main quest as a young assistant professor trying to make their mark at the LHC. In 2018, I hosted this workshop called Triggering on New Physics at the HL-LHC, and we invited all of these theorists to come with us, or to come discuss with all the experimentalists who are putting the triggers online, and give us some ideas of some crazy signatures that we're missing. And so one of the ones that I really like, actually, is called the soft unclustered energy patterns. So here we have a standard CMS event display, I put some ideas of, you can read more about this in a wide variety of phenomenology papers, but here's what a standard CMS event display would look like, and here's what a soft and clustered energy pattern would look like. So soft and clustered energy patterns basically have some sort of kinetic mixing with standard model particles, but you'll have this diffuse spray of particles throughout the detector. But when you're trying to distinguish between this and this, it's actually quite difficult. Another signature that I like quite a lot is called emerging jets. Again, a situation where you might not have tracks in the middle of the detector like you normally would. You're going to have some sort of, some sort of kinetic mixing with a dark sector, and then mixing back into the standard model, and you'll have some delayed production of standard model particles, which will look diffuse, and again, difficult to reconstruct, and also extremely difficult to trigger on, okay? And so the limitations, of course, of the traditional triggers, we could try to look at those directly. The limitation of traditional triggers, of course, is that we risk model bias. And we can either think about the physics that we want to trigger on, and we can detect it. We can think about the physics in the collision, but then our overlap is all these known or hypotheses processes. So what if the physics that we're looking for is outside this range, and is something that we haven't even really thought of before? And so that is where I believe that machine learning is going to, well, this is where machine learning is a little bit coming to our rescue, trying to look for, instead of relying on these known topologies, trying to look for something that's a little bit more anomalous or different from the overall background, and just looking for rare anomalies instead of trying to define our signatures. So the next point, I will go through a 5-minute deep dive on neural networks and autoencoders. So my guess is that if you are under the age of 35, you don't need this at all. If you're over the age of 35, you can probably go play on your phone for a little bit. If you're over the age of 35, then maybe a 5-minute deep dive, unless you're Lucas, and then you're fine. You don't need a 5-minute deep dive. And probably don't need a 5-minute deep dive on neural networks and autoencoders. I know you're teaching the class for everybody. So so this was my conjecture, at least at Princeton. Maybe it holds through at Brown. Anyways, I'll go a little bit quickly. Feel free to slow me down if you would like. So how do neural networks work? So the simplest neural network is just a linear fit, okay? So you have if A times X plus B equals Y. You have some free parameters in the fit. You have your input values that are X, free parameters are B, and your output values are Y, okay? With a neural network, we've actually renamed these to be weights. Weights are input parameters. We have our free parameters in the fit. A is our input values. We have a bias, so some offset, and then we have some output values, okay? So weights and biases. And so again, you can think of this as just fitting a straight line through data, just like we've done since high school. And so you can also, of course, extend this to n dimensions and fit all sorts of different planes, for instance. No issue to extend this to multiple dimensions. But the trick with neural networks is that if we take a linear output and pass it through a nonlinear function, or what we call an activation function, we can also start to approximate any sort of function, not just lines, but curves, steps, complex functions, things that become very, very difficult to model otherwise, okay? So we put in this activation function, and activation functions will allow us to make a better fit to any sort of data set that you want. This nonlinear activation this activation function has many different choices, but we often use these rectified linear units, ReLUs, in the simplest and most common form. But of course, we have hyperbolic or sigmoids, binary steps, etc. And all of this is taking inspiration from neural networks in the brain, where you have different layers of neurons that are actually going to be making some sort of computation, then either passing on or not passing on to the next layer, so we can make a generalized decision. And so with the same model, we can take the output of one activation plus linear transformation, and we can add another, and another, and another. And so without the activation functions, we lose structure. So a linear transformation of linear transformations just collapses down to another linear transformation. So by using these activation functions, we can actually start to fit all sorts of data with all sorts of distributions and make this extremely generalizable. And that actually is why I've really been enjoying. This is why I love machine learning, is the generalizability of these of this overall functions and networks. I think this is really the key here that actually maybe kind of fall in love with machine learning. And so with a simple feed-forward network, basically this is easy. We just take the number, we take maybe some handwritten recognition, we pass it through we pass it through some neural network. Every line indicates that every output from one layer is included in the transformation to the next layer. We have some activation functions, and we have weights and biases at each of these layers here. And then on the output, we'll have a probability of whether or not, for instance, of what number the input was. So for instance here, we have something written like a 7. If your neural network is trained well, then you'll have a high probability of it being a 7 on the output, okay? And so I'll so how do we get there? So so one more minute on training. So with a simple feed-forward neural network, during training, we have a large amount of data. So with some sort of truth label. So we have a handwritten 3, we tell that it's a 3. We have a handwritten 1, we say it's a 1. And essentially what happens is we start any neural network with a random weight, with random weights and random offsets or biases. Your initial results are poor. Okay, so if you have 7, you put it through this, okay, maybe it'll be 20% likely it's a 7, it says 60% or 70% likely it's a 6, it's just not very correct. So what we do then is that each time we train, we start with these random weights and random offsets. We calculate what our value is going to be, and then we calculate an error or a loss, and then we go back and we back propagate. We calculate the error for each one. We back propagate and determine the effect of the weight or bias on the loss, and therefore go back and update the weight and the biases as we're going through. And so by doing this in iterative fashion, so for each time we pass some data through the training, we have a weight, we have some effect that weight is going to have on your loss, and then you're going to update your weight to your new value, basically simple division. And we do the same with biases. After many, many, many iterations of predicting, calculating the loss, back propagating errors, and then updating the weights, we get to the value that we actually want. And so eventually we're left with a neural network that will hopefully perform pretty well with image recognition, okay? With autoencoders, which is what we put online, this whole structure actually, it's quite similar. We have an encoder into some small space, and then a decoder. So the encoder side is something familiar to us. The decoder side is basically this in reverse. This shrinks it to a pinch point. And for this, we actually go ahead and define our loss as a mean square error between the output and the input. Okay, so that is just going to be the difference between this output here and this input here. And we can train the autoencoder in a similar way, updating the weights and the biases as you go through, and eventually be left with an autoencoder that basically tells you, does this data look like something I've seen before, or is this going to be something new and rare? So a low loss signatures that we see often are a low loss, and signatures that are quite rare are something that are going to be a high loss. Okay? So, takeaway, which is again why I am pretty excited about what we're able to do with all of this. So this is flexible. We can represent many different types of algorithms. So you can have one neural network, you can train it for image recognition of a cat versus a dog, or handwriting, etc., which is fantastic. We can also use it for things like anomaly detection, depending on how we put together our networks. Also possible supervised searches for model-dependent signals. And this has a scaling advantage because you're not doing things like searching through lists of particles. We're not doing clustering. We're actually we have these feed-forward, the ML algorithms typically scale linear with the detector occupancy or number of channels. This actually gives us a very flexible way to create algorithms that will do exactly what we want. Caveats are, of course, you have to know your data, you have to test your edge cases. Interpretability and validation are also things that are still hot R&D product, hot research and development projects, even across machine learning spaces, trying to avoid black box and pitfalls. But the generalizability is quite impressive. Okay, so autoencoders. So the summary. So I'll just do a quick information about what we managed to do at the LHC. So we put online the calorimeter image convolutional anomaly detection algorithm, what we like to call Cicada. So our input was raw level 1 calorimeter data. So over here you can see a 2D image of a calorimeter event, an event as it looks through the calorimeter. Essentially, we did a similar thing. We had an encoder, we have the vector representation, and we have the decoder. Our anomaly score is essentially our mean square error. The difficult thing about this is that actually putting an encoder and a decoder online takes a lot of work. So with the implementation, we ended up using knowledge distillation. So essentially, this means that we have a teacher network that looks like this. And we have a student network, which can be much smaller and simply learn from the teacher. So we trained a teacher network, does a full encoder, vector representation, and decoder, calculate the mean square error. We have an anomaly score, and concurrently, while we're training the teacher, we're also training the student. And the student simply is a two-layer neural network, convolutional neural network, that simply is designed to take this two-dimensional image and try to calculate directly the mean square error or the anomaly score. And so this anomaly score is essentially our discriminator at what we put online. And so if we have a high anomaly score, we say, okay, we're going to trigger on the event, we're going to keep it. If it's a low anomaly score, we'll pass it by. It's probably something that we have seen before. This over here is called knowledge distillation. It's used heavily in DeepSeek, but I like to tell people that we actually used it first. So we had this online before DeepSeek actually published their papers. I just want to emphasize that, it's one of the places where we have a huge crossover between the work we do on CMS at Atlas. We are a system where we have very, very, very high constraints in terms of what we want to do and what we're able to do. We have 3.5 microseconds. We have, thousands of terabytes worth of data, hundreds of thousands worth of terabytes of data per second, and we want to do that very quickly. Right now, as we're going, one of the number one things I hear about in the New York Times is all these data centers. And so you can imagine that if you can find ways to do inference with lower power at higher efficiency, this is a place where things like this, where we're trying to do highly constrained computing, can translate directly into perhaps reducing the amount of energy that we need to power our data centers, or reducing the amount of pollution for the environment. So to put this online, like I said before, we had 3.5 microseconds from the event, which we see at the CMS detector, passing it through the level 1 trigger system. Then we have to get it back to the CMS detector and tell it we're either going to read out the data or we're going to pass it by and throw it away. So 3.5 microseconds to get through all of that. And just to keep in mind, it actually takes about 3 nanoseconds for light to travel a meter. And so you can imagine that we have 150 meters. It takes about a half microsecond just to get the data from the detector itself over to our counting room where our electronics are living. So this is really a non-trivial problem. We also don't want to put our fancy FPGAs in a radiation environment. Well, as much as possible, we do have some over there. But you can imagine that there's some pull and push there in terms of what sort of on-detector data processing we want to do. So essentially, at 0 microseconds, the data is read out from the detector. Around 0.5, between 0.5 and 1 microseconds, we start to digitize the data on the in the trigger primitive generators in the counting room. After about 1.5 microseconds, the data starts to arrive at the calorimeter trigger, so you can see all these fibers that are being input. We're trying to concentrate it into one place. This is all data from the calorimeter systems. The blue is actually from the electromagnetic calorimeter, and the red is actually from the hadronic calorimeter. I didn't have to plug those ones in. I did have to plug other ones in. And then finally, at about 2 microseconds, all this data is finally pooled in our FPGA electronics and starts to be able to become available to be sent to one board. So all of this data is going into 3 different layers of electronic boards. It's concentrated in this card. So you can imagine we have all this data coming through the backplanes. Then it's being transferred. So we're coming in through the fiber optics. Then it's being transferred to the backplanes, concentrated in this single board here. And then we're sharing the data across these multiple layers here, so we can concentrate the entire event into one board. So this is all things that a little bit tedious to have to manufacture all of this and to plug everything in and come up with a design. But the beauty of all of that is that at 2.5 microseconds, all of this data is concentrated into a single card. And then from there, we have at 2.5 microseconds, data is concentrated in our card, and then by 2.75 microseconds, we have to send it back out. So that gives us exactly 250 microseconds, or 200.25 microseconds to actually do our 250 nanoseconds to do all of our anomaly detection algorithm. So in this entire line of time of latency that we have to actually perform this, my algorithm, or our algorithm, Cicada, lives right here. We put everything into, concentrate everything into one card, perform our anomaly detection algorithm, like I just run it through Cicada, and then we decide whether or not we keep it or we throw it away. Okay, so I'll just flash 1 or 2 slides. I'm done at, what time do I finish today?
3:15.
3:15? Okay. Okay, good. So this is these are the first 2, my engineer Luis Alberto Perez Moreno and Chloe Das, who worked very hard on this implementation. Now I'm going into a bit of the nuts and bolts. These algorithms are built entirely in high-level synthesis C software. The core firmware built by Luis is in VHDL. But again, our algorithms are in C. So how many of you know C or C or C++? Okay. So now you too can program an FPGA. And so this is the first time this was actually done like this as CNS. And so all of these algorithms just live right here. Everything, all this other stuff that has to be done, trigger protocols, DAC readout, link stability monitoring, all extrapolated away. Our algorithms live here, written in C synthesis. Okay, not exactly C++, but almost C. Something that, if you know C, it's readable to you. And really, also with HL-LHC, but also, really takes us a step from having to program every single byte, every single bit flip by hand to saying, this is generally what I want to do, please make it for me. And I'll talk about one more place we're doing that for the future. Cicada runs in about 93.75 nanoseconds, or about 15 clock cycles, and was able to go online last year. I feel like this is a part of the colloquium where people get tired, so I like to show pictures of people's faces who have contributed along the way, just to put another human element in it. So this work was started actually with a theory student from Mariangela Lazanti, who was working with me on their experimental project. And he did the first, Sandeep did the first concept of, let's see if we can do some anomaly detection on general calorimeter image recognition. That turned into an Eric and Wendy Schmidt Transformative Technology Award, where we hired postdoc Adrian Pohl And then Luis started working with us to design the firmware so that we could basically extrapolate out all of these ancillary functions and just keep the core algorithms in high-level synthesis, or build them with high-level synthesis. We finally plugged in around 2023. You can see all the eye diagrams here. We had to do some tuning of the eye diagrams to actually make this go all online. This was basically an issue with the fiber cleaning. You can see above versus below. The eyes, and the ones that really look like the eyes of Sauron, are not good. These eyes down here, these eyes down here are good. You want a nice, it's a digital signal, so you want a nice big bucket between each of the sides. In 2024, we had the online software and online and offline software ready. We plugged everything in 2024, and then we got the first data at the end of 2024, and we collected for the full run in 2025. And next year, we're actually expected to get quite a bit more rate, considering what physics signatures are able to be picked up with this. So we're targeting a 1 kilohertz rate for 2026 for the Park data set, for those who are interested in this. Okay, or no, yeah, I'm happy to explain this in a little bit more detail. That's a little bit more for my CMS colleagues. I just would like to show a little bit about the results. So again, we trained on billions of randomly sampled background events. So this is random data that we collect anyways to study the trigger system. So we need to be able to calculate our rates by collecting all this, what we call zero bias background events. You can see those distributions in blue. We have the teacher anomaly score here from 0 to 256. This is actually because of how we defined the bits at the time. And you can see the difference between soft underlying energy patterns, Higgs to long-lived, TT bar, SUSY, Gulu, HB, Gulu, 2B hadrons, and a Higgs. And you can see the difference between this blue. Start to realize that maybe we can use this as a trigger because we have a higher acceptance for these interesting signatures compared to the background. Although I will say this is not negligible over here. These still actually create, because you have so many more zero bias events or more QCD events than you do electroweak. This is still quite actually a big deal. Our student network looks like this. It's a little bit smoother. There is a area of research. The student score actually does a bit better than the teacher score in a lot of places, which I see some of the students smiling about that, so that's great. And part of that is the idea that maybe it's learning from about the soft labels from the teacher, but that's something that's been noticed in a lot of the machine learning journals. And so we ran this alongside the standard triggers for comparison for some amount of time, and basically found that our rate estimates were correct. And we have since actually updated the training to improve for 2024 and 2025 and 2026. Here is a comparison if you just compare it to a standard HT or cut-based trigger of some various soft unclustered energy patterns, long-lived particles, etc. So again, x-axis, the trigger rate in kilohertz. This is how we measure. Kilohertz is around the range of what we can select. This is 10 kilohertz usually. They won't give you that much. They might give you something along the line of 1 kilohertz of not pure rate, just to give you a little bit of setting. And then we have the signal efficiency. And so, for instance, we are improving quite a lot on these soft unclustered energy patterns by looking at the entire event. And so there's a few places like that where we're improving significantly compared to the background, or compared to a standard HT type trigger. One other place, this is cicada score is, you can see the correlation with the cicada score. So this is the student score versus the teacher score. The cicada score also does a little bit better here. One reason for that is we do need to, when we're training the student, we actually do have to weight a little bit more highly the higher scored events, simply because we don't have as many of them, and we're trying to really train for the tails, because that's actually what we are trying to select for. So that is also somewhat biasing our trigger performance and what we're going to collect. Okay. This is from our first data run. I'm happy to discuss this one as well, from 2024. And you can see how we're performing during the run. Somewhat smooth with a little bit of decay. And then we have our top quark detection with Cicada. So basically here, at the LHC, if you have gluon decaying to two top quarks, you could have one top quark decaying to a B plus W's that are decaying to quarks. And so what we did as a study is we took this reconstructed top quark invariant mass. This is what it, we use this with a zero bias background. So this is what it would look like if we just had the QCD background with no cut on the Cicada score, trying to get the top 3 PT jets. And then if we apply a Cicada score of greater than 115, you do start to see some peak around 174 GeV, which is the mass of the top quark. So so currently actually, this is all from 2023 and 2024. We're currently developing the analyses on these data to try to do these generic bump punch searches and using known but rare standard model signatures as our standard candle. Okay, so this is one of our event displays. It's a proton-proton collision event that was only recorded by Cicada on October 10th, 2024. This, due to busier events tend to be favored. It would be interesting if we had time to try to reduce the correlation with energy, I think, if you could try to just go for pattern and shape recognition instead of also taking the energy in, but it's something worth thinking about and studying for the future when we determine which sort of anomaly detection algorithms we want to put online. But still, these these highly energetic events, I think, are at least interesting, even if it is standard model QCD, because this is clearly a very, very busy and interesting, very, very busy event. Looking ahead, we're going towards, here we are in 2011, 2016, so we had something like, 25 proton-proton collisions for bunch crossing. We went up to 30 and 40 in 2016. This is during run 3, or 50, run 3. This is more like run 2, which is about 40. I did get the numbers right. We're around 60, I think, right now, and this is what we're looking at for the high-luminosity LHC. So the entire trigger system is currently being upgraded. Brown University is actually leading the charge on some of this, in particular, one of the most important aspects, which is the track trigger, which can only be done because of the outer tracker improvements. And so we will soon be having tracking information online, courtesy of your colleagues here, which is pretty exciting. Okay, Future Collider I'm happy to talk about, but it's not the main focus of the talk today. So the last thing I'd like to leave you with is that, where are we going next? I mean, when we go from this to this, we're going to heavily be making use of AI at the high luminosity LHC. It's going to be online, it's going to be offline, it'll be in our data monitoring systems for operations. We're going to be putting it everywhere in the level 1 trigger. We're going to be putting it even for where do we transfer data and when, to which computing sites. And this is also courtesy to the next generation trigger. One thing I'm particularly excited about now, which I think I told a few people about when I was discussing things today, we're developing logic gate networks for ML, which we are hoping will improve performance further. So in particular, I was talking about how if you choose, you'll vary the weights and the biases so that you choose the right functions. We're trying to change that to actually picking out the correct combination of logic gates. So really trying to reduce the amount of multiplication and these complex functions that we have to put online, and go directly to, okay, it's not the function we're putting online, it's actually these core logic gates in this series that will be each of our layers within this neural network. And so I'm happy to pass along some of the work that we've just started to do on that, which we're hoping to put online for the HL-LHC and maybe for smart pixels as well. And right, future detectors will require lower power devices, faster data filtering, but also I think all of this is going to be useful for other things like, all these ML, large language models that we're using. And so in summary, CMS was the first to put autoencoders for anomaly detection online. Atlas has now been online, so it's no longer, it will be soon. I think they just got online last October. Okay, so we have currently a 50% overlap with current triggers. Any questions? I'll leave it there.
Thank you.
So, correct.
Okay.
Thanks, Isobel. Very nice. I have one technical question and one more real question for strategy. So technical one is you use the knowledge distillation basically to save the decoding process. You work in latent space.
Yeah.
There are more elegant ways of doing this, like variation autoencoders. So have you thought about using them?
Oh, yes, definitely. Definitely we thought about different mechanisms. If I'm completely honest with you, part of this is we needed a hammer, and we found a hammer, and so we found a way to reduce it. So knowledge distillation was actually a very easy and straightforward way to do it. The variational autoencoders, the issues with the variation autoencoder, I think that would still be, so that's what our competitor, Xaddle is doing. And so that it was, we have a large number of parameters, and so we were worried we wouldn't be able to get the variational autoencoder to work with, because we have like
it all
10
depends on
bits.
the size of your latent space, right?
Yeah. So we did not test a variational autoencoder with this. We found that the knowledge distillation worked, so we didn't really fully test a variation autoencoder. It is an interesting, it's an interesting idea. The first thought that we had was that this isn't certain to work because of the number of parameters that we have at input. And this one did work. Mm-hmm.
Okay, and then the real question. So you showed this event which was triggered just by cicada, not anything else.
Yeah.
So say you have a collection of 100 events at the end of running. What do you do with them without a model?
So right now So right now what we're doing is we're doing model independent bump hunts. And so that's.
But what if it's SUPS which doesn't have a model?
Well, so the bump is great, right? Because that gives you some. The bump is great. It's a bump hunt, exactly. But I mean, so people are actually doing this with. Well, it's more or less a bump hunt that you do with a. But you do it in some sort of parameter space, like a neural network parameter space. So I think overall, if you. Okay, so I mean, so you determine what the background distributions look like from sideband regions, and then you decide whether or not what you're seeing is a signal over background. I would akin this to any of the Higgs searches that we had that used discriminator score as our
right. But the problem is that you always have the signal model. Right?
You always have the sideband.
Model, right? So all you can say is that these events are anomalous in certain parameter space, and you cannot even say if event A and event B come from the same type of process, right? The anomalous would be completely different.
Yeah, in the end, what we're targeting first is to look for things like emerging jets. So you're asking if not a bump hunt and not a signal space, then how are you going to do a search for it? I mean, in the end, if we can't determine a single physics signature, then I don't. Yeah, if you can't create a new trigger based on what we found with this trigger, then I don't necessarily believe that it is anything interesting or worthwhile.
So if it's not a bump, it's kind of like a scouting expedition where you would install these specific triggers to recognize.
Exactly, to see whether or not we can figure out a pattern in what we're seeing. I think in the end, if we don't figure out a pattern in what we're seeing, then it's possible we're not modeling the edges of tails, for instance. But I think that we'll be able to see that in terms of what the distribution should at least look falling. But yeah.
Presumably, first thing you would see is some emerging hot cells which are not blanked out. Have you seen something like that? Can you use it as a
Emerging.
monitoring?
Yeah, we do see that to some extent. And so with the emerging hot cells, so actually we don't. So it's actually, I know that you're thinking more about the signal side, but even from the point of like detector quality monitoring, it's something that you do see a slightly higher score. So if that is if you have, for instance, hot cells or bad channels, you'll see this showing up in cicada. You also see it showing up in other detectors as well. If we see that, we'll have to filter out those channels, for instance. Yeah, I don't know if I did a good job answering your question.
Use it.
No, can
you find the hot cells?
Exactly, you use it to find hot cells. Exactly. Yes, definitely.
So
yeah,
you haven't
yeah.
really like plot the map of frequency of your cicada anomalous events.
You mean in
you
terms
would see
of
some intermittent hot cells or bad cells on this plot, right?
well,
Just integrate over the.
I have some plots that I want to show you, but I don't. Yeah, so one thing actually that was kind of funny is that we trained cicada. I might even have these plots in backup. I probably should. Well, yeah. So this is fine to show because we trained cicada, and then basically I had a summer student who came along and I shouldn't tell. I'm going to get myself in trouble. Anyways, it's fine. Basically, I had them inject energy into each of the cells. And what we did find is that some of the cells behave differently than other cells, and which gives you an idea that we're not completely calibrating the detector evenly. So probably shouldn't say that in front of people who are going to ask me to fix it. That was the I probably was fixing it. So basically I had my summer student basically took the same amount of energy and put it across the detector in various cells and then found interesting patterns. And in particular, do I have it? No, I don't have it in this slide, I think. But in particular, he found that there were some cells that were more sensitive to energy deposits, and it gave you a higher cicada score, which would then make me think that the calibrations for the detector need to be slightly modified.
Okay.
Well, definitely the training.
Other people who have any questions?
Mm-hmm.
Yeah.
For the emerging jets, did you do any kind of like ablation study or something to see like how long lived, like what times you're sensitive to?
I mean, yeah, and this is where we play a bit of a game. Well, yes. So we play a bit of a game, and we do sometimes target signals that will develop that will be decayed, particularly in the caliber that we're interested in. So. It's throwing some dice and trying to pick what you're interested in. Yeah. But we're going to start in on that analysis this summer, actually, after we finish our generic bump hunt with AXO. Yeah. Mm-hmm.
Okay, Matt?
Mm-hmm. Yeah, I had just a quick question about the emerging jets, actually, as Jan asked about it. So cicada only gets calo information.
Mm-hmm.
So how does the sensitivity to the emerging jets model come in if it doesn't know anything about the tracks or the lack thereof?
The jets are actually seem to be more displaced, or sorry, not more displaced, to be broader, and some of the models that we're looking at. So, so it's just basically the overall distribution. Yeah. So
the calo granularity is sufficient to tell that apart.
Yeah. Because at least it could get those are at the order of like 0.1 eta in
Okay.
Yeah. Okay.
Cool.
Okay. Any other questions? One last question.
I just want to make sure I understand the anomaly scores.
Yes.
Is it that you're taking like a set of zero bias data and using that to train the autoencoder, and then it's going to like do a bad job when it sees an interesting event, so the loss will be high?
Yes, exactly.
Oh, okay.
Yeah. So basically, I think I heard you. So basically, yes. You are if most of your events look like so if most of your events just look like, I don't know, like a normal QCD background where it's just this smooth distribution with some, low energy deposits, then that will be reconstructed really, really well because it sees it all the time. Yeah. And then if you have some with, a broad distribution of like 10 GeV energy deposits, then that's something it doesn't see as well and does not do as good of a job reconstructing it. I did take out of this presentation, we had some loss plots as well, so you can basically see like where it's doing a bad job and really see these. It can point to that in particular. Yeah.
And I'm assuming you don't like tamper with the training data at all, because any like interesting things, the rate is so low, it doesn't matter.
We tamper with the training data at all. You mean in terms of taking out standard model backgrounds? Yeah, this is an interesting question. So this was something that I think it's not something we didn't feel comfortable we had 2 anomaly detection algorithms online this year. And so actually taking out standard model data sets and training against those and putting those in your like background might be interesting. No, I think it would be interesting. It'd be great. And even saying, okay, only trigger on things that are not triggered by the rest of the trigger would be also another interesting thing to do. We could get a higher rate that way, and we can lower anomaly threshold. But there's a lot of tweaking and parameter space you can do there. So we didn't do it this time around. It's something that, yeah, I'm really intrigued by though. So, but we didn't do it. Yeah.
Okay.
Mm-hmm. Mm-hmm.
All right. Good.
Will you flip the algorithm and actually look for things? I mean, if you said in the next one, we'll replace all the triggers with something that works this way with this kind of hardware, but you'll certainly want to recognize particular patterns.
Yeah.
Whereas right now you're recognizing that no pattern. You're selecting that you recognize no pattern.
Yeah.
But I mean, it should be quite powerful used the other way around.
Yeah, exactly. Actually, it's so in terms of either training on samples we know about is another. Actually, that is what I'm kind of hoping people take away from this is that now that we have access to these tools, you could train for all sorts of things. And it's really almost the sky's the limit, and especially because these algorithms are so flexible, you could just change you can change completely what you're trying to look. What your image reconstruction even means. So it's exactly that. You want to flip. Either you want to say, I want to look for this specific, maybe I want to look for soft unclustered energy patterns, and I want to explicitly look for that. You could put that online. You could say, I want to count things with this number of jets. You could also say something like, I want to pick out the anomaly scores that I saw in run 3 and try to find them in the HL-LHC. So all these things are, and so that's, if I'm honest, I probably shouldn't criticize this after giving you a whole presentation on it, but I think this is like the minimal thing you can do. It's like the smallest step, and all of this is just, we have a huge amount of flexibility to do a lot more, which is I'm excited about. So, yeah.
Very nice. Thank you.
Yeah.
All right, one more question.
Mm-hmm.
Okay.
Yeah.
This is kind of piggybacking off this, but also you mentioned the smart pixels and the moving towards like
Mhm.
hardware.
Yeah.
So there you wouldn't have that same flexibility though, because you can't really like retrain.
Not really. So the
then
thing,
you would still
yeah.
want to have more of this like general approach, or would you?
Well, this is why I actually even got more excited, is because in 2025, so we had to retrain everything from 2024 to 2025. We kept almost exactly the same architecture, even though our distribution of pileup looked different, like almost 100% the same architecture. So I think so I'm really interested in is trying to figure out how to get these logic gate networks to be that flexibility where you could, So Lino and I are discussing this currently of like what I would love to have some summer students just, throw some crazy ideas at them and see what we come up with. So
Try to get that flexibility.
yeah, because I was actually almost shocked that we took exactly the same architecture, trained it with a different pileup distribution, and the architecture itself stayed exactly the same. And so we were able to put it back online. It was actually kind of a scary process because we were trying to adjust for different runs. The conditions change. So how is that going to affect your neural network changing? And you don't really want to rewrite your firmware every single time. You'd rather just update weights. So I'm kind of excited about where that will run. It just takes time for R&D. Yeah, but it's like, I think that's one of the most exciting directions this can take. So yeah. Okay.
All right.
Thank you.